winter term.
Do we play teams twice? It's like the same.
I want to say it's Valentine's that we play them again.
It's 221.
221?
Yeah.
Oh, yeah, you're right. They play Roseburg on Valentine's Day. All right, so a statistic comes from a sample. A parameter comes from a population. We use the statistic to estimate the parameter. When we're working with proportions, our statistic is p hat, parameter is p. When we're working with the mean, our statistic is x bar, and the parameter is mu. So today we're going to look at a population distribution, a sampling distribution, and then a distribution of sampled data. We are going to toss coins again today. So raise your hand if you need a coin, and I'll bring you one. If I can remember where to hit Don't lose your money. All four of you? Bianca.
Because you dropped the first one, I tried to dodge it, and I need one more coin.
No, you just need to pick up that one. It's supposed to be Nolan, that one, because it's all gross on 34. That's all I got. You got pennies.
That one looks good, so I'm
You need one too.
I was like, oh.
heads or tails?
No. Heads.
Yeah.
Wait, you gotta do that. You gotta do that.
I was like, no, then I heard
Oh,
it.
still heads. I did it wrong.
Wait, how was the winter formal?
It was gonna get dance.
I thought it's super good stuff.
It was super late at first.
I thought it was for freshmen.
So I showed up like 30 minutes late. So
Was it a freshman?
All right, you're going to toss the coin 20 times. I want you to record the proportion of heads you get. 20 times, record the proportion of heads. I can flip a coin.
What? Did you even get the thing right?
4, 5, 6,
I remember like 2 weeks.
I know, but it's his birthday.
10, 11, 12, 13, 14, 15, You got 7 out of 20?
I tried to
That's it?
get it, pick it up. I was like,
Are you done, Emma? Emma. Emma.
am I doing the right thing?
Emma.
Why is it asking me all these questions again? I did all this.
Which one are you?
I changed those drawings last year, and it was only $180. But now they're all $200.
Yeah, the cost of everything has gone up.
A quick 2 months.
I know.
Did it.
Okay, wait.
I just keep doing it over. I'm done.
Oh, he's done.
He's done.
I just like.
He's done. All right. Anybody need more time for flipping? Oh, Nolan does. Nolan does. Come on, Nolan. All right. So, what is the population that we're looking at here?
20 coin tosses?
Not 20.
Oh, the
That-
heads.
No, I like the coin tosses, but is 20 the population? Are there 15 of us? Did you forget about me? I cost coins too.
I'm so sorry.
I tossed coins too.
320.
Thank you. So you're getting closer, but that's still not quite it. That's still a sample. Do coin tosses, now that I said it backwards once, I have to rethink every time. Do coin tosses happen outside this classroom? Yeah.
So
Do they happen all the time?
Yes.
millions.
Millions upon millions. So to make it easy, let's just, I know, right? Every time there's a sporting event, there's a coin toss. So we'll just say all coin tosses ever. Because we don't know how many there have been. Now, Lindsay, what were we focusing on? What were we counting? The amount of heads. So the parameter is the proportion of heads for the coin tosses. And what should the proportion of heads be? Half. So we would say P is 0.5. What was our sample?
This classroom?
Smaller. How many did you do, Shania?
20.
20. So we took a sample of 20 coin tosses. So we found a statistic because we were looking at a sample. And so the notation we use would be P hat. So when I did my coin tossing, my P hat was 12 out of 20, or 0.6, because I got 12 out of 20 heads. So you're going to have a different P hat, unless you got 12 out of 20 like me. But your P hat depends on how many heads you got. So your number here should possibly be different than mine. It could still be the same. Everybody good? Now we're going to put everybody's samples together. Issa, are you doing a coin toss on Google? Do 20 coin tosses on Google really quick. Count the number of heads. Just Google coin toss.
Oh, just ask Lindsay. She already did it on the there.
Yeah, just go to Google, or you can do it. All right. So mine was 0.6. We're gonna make a list of everybody's P hat. So Kitiara, what was your P hat?
11.
As a decimal?
Oh, it's this one. 21.
11 out of 20 is 0.1.
0.55.
I know.
Yeah.
I wanted her to get there.
Oh. I have the same ones.
0.55. Seth.
0.4.
Lindsay.
0.2.
0.2.
I got 4 heads.
Wow.
They use Google.
That's crazy. Shania.
Sam, 0.55.
Anna.
0.6.
Annika.
0.5.
Aster. Miranda? Naomi? Wow, lots of 0.5s. Nolan?
0.55.
Bianca? Emma Jordan?
0.4.
Emma Almanza?
0.8.
Did you shake your head at me for saying Emma like that, Emma?
Me? No.
No? Yes, you did. Trey?
0.35.
Tanner? Issa, are you done? Okay. Did I miss anybody?
No.
How many heads did you get? 8, so you have 0.4. Alright, so now what we're going to do is we're going to make a sampling distribution. So we're going to graph these. And we're going to use a dot plot to graph them. And let's see if I can draw a straight line.
So did you get the credit
This looks like
Our lowest was Lindsay with 0.2 and the highest was Emma with 0.8. So let's go 0.2 to 0.8. That should work. 0.2,
Yeah, we see.
0.8. So that's 3, 4, 5, 6, 7.
Go for English? Oh, I don't know how to do English. My English is 0.2. But they said three.
when she didn't talk about it until we started her classes.
it's like winter and spring.
Did you get some Okay, I feel better about it.
Because I think we'll probably get like spring.
Yeah.
Alright, and then we do have some with 5, so we'll put the little hash marks in between each one. So then we're just going to put the dots above the numbers. I'm not going to walk you through that. You should be able to make your dot plot. Remember, just put the dots above the number line, not on the number line. It's so pretty. Our dot plots should match because we should have the same list of data. So it said make a sampling distribution below. This is the sampling distribution of p hat. Now, because of the way that coins are made, we know the parameter. What should the parameter, the proportion of heads be? 0.5. So, if we have a good sampling distribution, we should be centered at 0.5. Where is the center of our sampling distribution? 0.4 what?
0.44.
How did you get that?
Because there's like more on 0.4, but like it's mostly 0.4 and 0.5, so but it's like slightly closer to 0.4.
How many people are in here? There's 17 of us, right?
So
2,
the
6, 7,
middle-
9, 10, 14, 16, 17. So there were 17 pieces of data, which means the middle piece of data is what? 0.5 out of 17, so it'd be the ninth piece of data. 1, 2, 3, 4, 5, 6, 7,
Yes,
8,
nine.
9. Right here, 0.5. So this is centered at 0.5. So do we have bias? What is bias? Oh, come on, I told you what bias was last time. But it is your unit, Emma. Bias is when you overestimate or underestimate. Did we overestimate or underestimate the parameter? No. We actually did a really good job. So no bias. Most of the time when I do this, we do have bias. But you guys did a good job. Or you got lucky. You didn't over or underestimate P. Do we have high variability?
Yeah,
Yes. Why?
because it's anywhere between 0.2 and 0.8.
Yeah, our spread is quite large. It's 0.6. Do you remember what we do to reduce variability? Increase sample size. So if we increase our sample size, our variability should reduce. And then just because I told you that definition will be on the test, technically what we drew above is not a true sampling distribution because it only displays the samples from our class. Remember, a sampling distribution would be all possible samples of size 20 from the population. Well, coin toss population just continues to grow, so it's like impossible to get all possible samples of size 20 from that population because the population number stops growing. So it's not a true sampling distribution, but it is a sampling distribution of p-hat. Questions? Now we're going to look at a sampling distribution for averages. So that was proportions. Now we're going to do averages. So suppose we want to estimate the average number of siblings for all of the AP Stat students in this block. We will do this by selecting a sample of size 4. So what is the population here?
17.
That makes me feel good that you included me as a student, Shania. Technically, I'm not a student. So we're looking at all AP Stat students in this hour. So let's just say AP Stat students block 3. And we'll go with period 3 because otherwise I have to write more. What's the parameter that we're interested in? What are we trying to estimate? The average number of siblings. And with means, what notation do we use for the parameter?
Yeah.
You know. What is the sample?
4 students.
We're going to pick 4 students. And what statistic, what's the notation for average when you're estimating? It's not mu, what's the other one? It's X bar. Statistic, X bar, parameter, mu. All right, so we're going to go around. Everybody's going to tell you how many siblings. We'll make a list. In the past, I always get a question about siblings. Does that include step siblings, half siblings? If you feel like they're a sibling, you want to include them, include them. Okay? That's up to you how you count them. All right.
One.
So there's 2 of you, 1 sibling. Yes. So we are including yourself. So Kitiara there's her and a sibling, so 2. So you are just going to give me the total number of children in your family. Sorry, I did forget to say that. So 2. Seth. 2. Lindsay. 7. Shania.
Counting myself too.
2. Anna.
What? Counting myself, how many people, children are in the family?
I'm glad Annika knew how many were there for you, Anna. Annika.
3.
3. Aster. Miranda.
3.
Naomi.
5.
Nolan.
3.
I knew that one. Bianca.
5.
Emma Jordan.
2.
Emma Almanza.
3.
Trey.
3.
Isa.
3.
And Tanner.
4.
4. I know, right? That's unusual. Usually I have some only. There's 3 of us. But I'm not a student, so we're not going to include me this time. I did specify AP Stat student. All right, so we are going to make a dot plot. This is going to be the population distribution. So we're going to put all those on our dot plot. So let's see, the lowest to highest is 7. 2 to 7. 2, 7, 3, 4, 5, 3, 4, 5, 6, 4. 3, 4, 5, 6. So we have a 2, a 2, a 7, a 2, a 2, 1, 2, 3 threes, 5, 3, another 5, another 2, 3 more 3s, 1, 2, 3, and then a 4. So is this a sampling distribution?
Yes.
No. What's the population? Did I ask each and every one of you?
Yes.
So this is not a sampling distribution. This is a population distribution.
But there are some people who are absent.
Yeah, well, we will say they don't count for the population today.
Seth, they don't exist right now.
Yeah. So since it's a population distribution, we can find the true mean number of siblings for the class. So I want you guys to find the mean number of siblings, add them all together. There are 16 of you, so you're going to divide by 16. What'd you guys get for the average? 3.25. I got that as well. What notation? Mu or X bar?
Mu.
Mu. It's a parameter because it comes from the population, so we're going to use mu. So the true average number of siblings is 3.25. So now we're actually going to take a sample of 4 random students. We're going to find those averages. So we have, let's see, what color is going to stand out? So I think I'll put it below. So what we're going to do is we're going to have the calculator pick 4 random digits between 1 and 16. And we're just going to go in the order of how I asked you guys. 13, 14, 15, 16. Now, can you have a repeat student? I don't want to know that Nolan has 3 siblings twice. So you're going to use the random digit generator on the calculator. Do we remember how to get there? What did we press? Math. Prob. Number 5, rand int. 1 to 16, and you want 4. I was lucky and I got 4 different numbers, so I would take student 13, which was 3, student 16 was 4, student 4 was 2, and student 6 was 3 siblings, so I'd add those together. That's 7, 9, 12, and divide by 4, so I would get an average of 3. I suppose I should show that I divided by 4. So you guys are going to pick your 4 random students using the calculator. You're going to get a different average than me, and then we're going to go around, share the averages. Well, I suppose you might get the same average as me. If you get a repeat number in those 4 numbers, just pick a new sample. We don't want to know that Nolan has 3 siblings multiple times. Doesn't do us any good. You have to do a different one.
Well, no, you're adding up the, like, no.
Wait.
No.
Alright, so you numbered them right here. So that's number 1. Oh, you have 3. Oh, I was looking at that. Oh, so 10?
That was like
I know, me too. I was like,
I said it was 3.
so great. We should probably
5, 14, 16,
I know.
16,
Especially when he immediately was like,
14,
yeah.
5,
A good 8.
and 8.
What?
So 4, 3,
11.
3, and 3? I don't know.
So how many siblings?
Yes.
You gotta do a different one than what you did.
3.
The other one.
Sorry.
You didn't right. You don't know how to count. You didn't count.
I got myself like the 8
But you can't have yours.
What?
3.25.
You have 3? Oh, I'm waiting.
Yeah.
That's
2
perfect.
points.
I know, you got it perfectly.
It should be 1, comma 16, comma 4. Because that's the lowest number. 16, comma 4.
We have to divide it by 10 or by 4.
Yeah.
Which are finding the average.
My mom
So those
just
are your
cannot
4
write it all around
ones.
because the Organ Promise is called Organ Promise, not Organ Treaty.
You could
Why?
choose.
Just the working
And see if you get.
Did you
First
say
off,
one?
no, that's why I'm paying.
Did you get an average?
Yeah.
How did you get the 2 highest numbers? Way to go, Seth. Did we all get our average?
Yes.
I got 3.
Not 3.25.
Did you just copy mine down? Did you just copy mine down?
Huh?
Say yes.
I didn't even know that you wrote that.
Okay.
Yeah, I'm trying to confuse me. I'm so worried.
All right, so we're gonna go around again. You guys are gonna share what you got for your average. Let's see, I'm gonna start on the other side of the room. Aster, what'd you get? 2.75. You need to be writing these down as well. Miranda? I'm sorry, I didn't hear you. 3. Naomi? Trey?
2.5.
Isa?
3.
Tanner?
3.75.
Emma Jordan?
3.25.
Emma Almanza?
2.5.
Bianca? Nolan?
2.25.
Seth?
4.75.
Kitiara?
2.75.
Lindsay?
3.5.
Shania?
4.25.
Anna?
3.
Annika?
4.
And that was everybody, right? So we're going to make a dot plot of our sampling distribution now. So this time the lowest is what? 2.5. Highest is 4.75. So if we go 2 to 5, that should cover it, right? Yeah, but I'm weird. I like whole numbers. It makes it easier to make the hash marks. So yes, I am gonna, this will be the first time that my number line has space on the edges. All the others I was able to go low to high. So that means I'm gonna cut it into thirds, 3 and 4. It's not perfectly spaced, but, and then we need the hash marks in between for the halves and the 0.25s and the 0.75s because we have those decimals this time around. And then we're going to put our dots. So we have 2.75, 2 3s, 2.5, another 3, 3.75, 3.25, 2.5, 3, 2.25, 4.75, 2.75, 3.5, 4.25, 3, and a 4. And this time it is a sampling distribution because we are looking at the samples. Where is the center?
3.
3? So this time there's only 16 because I wasn't a student. So half of 16 is 8, so that's 3, 5, 7, 8. Well, actually, technically it'd be 8 and 9, right? But they're both there. So like Shania said, we're centered at 3. So do we have bias?
Yeah.
Yes, we do. Why do we have bias, Seth?
Because it's less than the actual mean.
So our estimation for the average was 3, and the true mean is 3.25. So we do have bias. We would say it's low bias because even though we underestimated the true mean, we're pretty darn close. What about variability?
Yes.
Why?
There's a lot of different numbers.
Yeah, there's actually quite a few different numbers. Our range goes from what? 4.75 down to 2.25, which is 2.5. Now, even though we labeled it as a sampling distribution, is it a true sampling distribution? Yes or no? 50-50 shot. No, why not?
Too small of a number? I don't know.
It would have to be like literally everybody. that has-
We would have to take every possible sample of size 4 from those 16 up above, which would be, if we figure it out, that would be 16 choose, 4, would be 1,820 samples we would have to take. Did we take that many samples? No. So we didn't take every possible sample as size 4 and find the average, so it's not a true sampling distribution. And then just to, hit it home one more time, we're going to do a fill in the blank for the definition of a sampling distribution. Can you tell I really want you to understand this? Said it's going to be on the test. I think I defined it last time. I talked about it on the previous page, talked about it here, and now we're going to define it again. I promise I'm going to ask you a question on this. Definition: a sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. May I flip?
Yeah.
We are almost done. Nolan's checking the time. He's like, it's my birthday. I have to do math.
Hungry.
Ugh, I'm hungry too.
You give me any food?
Did you get me anything for your birthday?
No.
No. All right. What makes a statistic a good estimator of a parameter? After we made the dot plots, what were the 2 questions I asked?
Display bias and the distribution display high variability.
Thank you, Trey. So we want to pay attention to bias, and we want our bias to be low. And then we want to pay attention to variability, and we want low variability as well. I used all caps, and I ran into my word. Sorry, variability. So, high bias usually happens because you have a poor sampling method. What are some of those poor sampling methods that we learned back in chapter 4?
Convenience.
Convenience. What else?
Like when
Optional response, what is that called?
Voluntary response.
We have that.
Like
Yep.
cluster or something?
No, a cluster could go either way depending on how you cluster things. But convenience and voluntary response are the two most common. Bad sampling methods. Then there's all the other things that can go wrong with good sampling methods. And then Seth reminded us the best way to reduce variability is to increase your sample size. So now just to kind of give you a visual of what those things might look like in a graph, we're going to draw the 4 possible outcomes for a statistic. That was not a straight line. That's okay. Let's see, what color? Let's go with purple. I like purple. So before we draw these, suppose that we are trying to estimate a proportion using a statistic and the parameter is p equals 0.2. So the first possibility is we have high bias. So we either really overestimate or underestimate the parameter. And we have high variability. The data is really spread out. So do you want to overestimate or underestimate?
Under.
Under. So here's the actual parameter, and we'll say, I don't know, we'll be at 0. So high bias would mean that we're more centered around 0. So we have a lot of data there. And then the high variability would mean that we just have a lot of spread. So we may even go past 0.2, and we have data all the way everywhere. We could even go lower into the negatives. High variability, big spread of data. High bias, the center of our data is not where it should be. In this case, we underestimated the parameter. Another possibility is that you have high bias but low variability. So just to stick with underestimating, we'll be at 0. Here's the actual parameter, so we're still going to underestimate, but our variability is going to be smaller. So we're going to have a lot of data right around 0. We really underestimated our parameter, but our data is nice and condensed. A third possibility is low bias, so we estimate the parameter well, but we have high variability, so we still have a wide spread for our data. So the parameter is p equals 0.2. Low bias means that we will be centered at 0.2. High variability means that we still have a wide range for our data. And then the last option, the best, low bias, low variability. We are centered at the parameter and our data is very compact. So we don't have a huge spread. Kind of looks like a Christmas tree when you do the dots like that. And then just a note, when you increase sample size, it helps to decrease your variability, but it doesn't do anything in terms of bias. Before you put it away, don't put it away yet, Lindsay. Okay. We're gonna look at a example homework type question, the exit task. We're gonna do it together. Can I flip?
Yeah.
All right. Did you say I guess? Geez Louise, Bianca. All right. Say what? All right, so we have the histogram on the left shows the intervals in minutes between eruptions of the Old Faithful geyser for all 222 recorded eruptions during a particular month. For this population, the median is 75 minutes. Fathom software was used to take 500 SRSs of size 10 from the population. The 500 values of the sample median are displayed in the histogram on the right. The mean of the 500 sample median values is 73.5. So, before we get too far into the actual questions, we are told that the histogram on the left shows all the 222 recorded eruptions, the time in between. That means this is our population distribution. Then they used a computer program called Fathom to take 500 samples of size 10, and those are shown on the right. So this is the sampling distribution. We're given two numbers in the paragraph. We're told that for the population, the median is 75 minutes. And then we are told that the mean of the 500 sample medians is 73.5. Which one is the statistic and which one's the parameter? 75 would be the parameter because it came from the population. Now, this question is also weird because we tend to use means and proportions, but they used median here. So for a parameter median, you use a capital M. For a statistic median, you use a lowercase m. So, is the sample median, 73.5, an unbiased estimator of the population median, 75? Do we have bias?
Yes.
We have bias. So the answer would be no, it's not unbiased. Unbiased means there's no bias, right? So That word right there means we have no over or underestimation. Underestimation. Our sample median, 73.5, underestimates our parameter of 75. So our statistic, and again, you could probably word this better, is biased because it underestimated. Any questions on that one?
So what makes it biased and unbiased?
Bias means that you overestimate or underestimate.
So what would that look like on the graph?
Same number. Right?
If we have bias,
Yeah.
so here our parameter is 0.2, and we underestimated our data is centered at 0, so we have bias present. It could also go the other way,
Because why would they name it?
like, well, of course, we don't have under or overestimation. This one also underestimated. We knew the true mean was 3.25 and we were centered at 3, so we underestimated.
So that makes it biased.
Yeah. So when it says unbiased, that means that your statistic and parameter are exactly the same. So that would be like this one with the coin tosses. We know the parameter is 0.5 and our statistic was centered at 0.5. So that was an unbiased estimator. Any other questions? All right, number 2. Suppose we had taken samples of size 20 instead of size 10. Would the spread of the sampling distribution be larger, smaller, or about the same? What does spread measure?
Would it be smaller?
It would be smaller. Spread is a measure of your variability, and if we increase sample size, we should reduce the variability. So we would expect it to be smaller. So spread is a measure of variability. So increase sample size should decrease variability. Any questions on that one? All right, last one. Describe the shape of the sampling distribution. Explain what this means in terms of overestimating or underestimating the population median. So we're looking at the shape of the sampling distribution. How do we describe shape?
Socks.
That would be
Oh, wait, no.
distribution.
Alright.
Shape's just the first S of
Alright.
socks.
Skewness.
Skewness or symmetry, right? So what do we have? Symmetry or skewness for the sampling distribution?
Skewness.
To which direction?
So that.
To the left, which means what?
High bias. Right, yeah.
If we have, what's the next letter in socks? Outliers. So if we have skewness, that implies outliers on the low side because we're skewed left, which would make sense that we underestimate our parameter. So we'd say skewed left. And that implies low outliers. Which makes sense with our underestimation. Am I off this screen? 'Cause I'm off my paper. Underestimation. Oh no, it fit perfectly. Questions? Nope. All right then. If you borrowed a penny, please, I'll come around and grab them. But